Hello everyone, my name is Jefferson Gil de Oliveira and I'm from University Center of Serra Gaúcha, and I would like to present you the results related to the analysis of liquid vapor interface velocity using optical flow method during two-phase flow boiling. These experimental results are provided by a partnership with Jaqueline Biacon Copete from University of Vale do Rio dos Sinos and Elaine Maria Cardoso from São Paulo State University. Well, flow patterns are found in many processes involving multi-phase flows in the industry. Several experimental studies have been reported uh, focusing on the characteristic of flow patterns due to their important influence on the performance of steam generators, evaporators, and condensers. So, the study of nonlinear fluctuations related to flow patterns and fluctuations found in pressure drop, for example, is a significant contribution to understanding the flow patterns and the instabilities related to the influence of interface velocities and phase velocities too, observed in two-phase flow systems. In particular, many authors have focused their studies based on the dynamic of flow patterns, including superficial velocities and the behavior of liquid vapor interfaces. So, the motivation for this study, in fact, is related to the analysis of the nature of flow patterns and the influence of the liquid vapor interface dynamics. But we can say that even considering that many studies have been reported in literature focusing on the behavior of flow patterns, there is a considerable lack of investigation on the nature of such behavior during flow boiling, mainly in small channels. Well, the experimental facility. Um, we developed an experimental setup to investigate flow boiling, pressure drop, and flow patterns in a horizontal small channel. The experimental system consists of a loop that provides controlled mass flux, and it was designed to test different fluids under a wide range of flow conditions. And the main part of the loop has a preheater, a test section, and a visualization section. The preheater, in this case, established the experimental conditions entering in test section immediately downstream. It consists of a horizontal stainless steel a tube with 1 millimeter internal diameter, a total length of 515 millimeters, and a heated length of 440 millimeters. This tube is uniformly heated by Joule effect, and the intensity is controlled by a power supply. The test section consists of the same tube and the diameter, and same tube and diameter, with total length of 366 millimeters and heat length of 265 millimeters. As well as the preheater, the test section is heated by Joule effect, and the intensity is also controlled by a power supply. Here we can see the visualization section downstream of the test section with 136 millimeters length glass tube with the same test section internal diameter. Both preheater and test section are thermally isolated, and the refrigerant enters the preheater to establish subcooled conditions in the inlet of test section. we have the measure of temperature and pressure using absolute pressure transducers and thermocouples in the preheater inlet and test section inlet to establish the pressure drop in the test section. We use a differential pressure transducer in this case. Well, experimental parameters. In this case, we used isobutane, considering a saturation temperature of 70 Celsius degree, a fixed mass flux of 890 kilograms per square meter second, and a heat flux ranging from 5 to 6 to 20 kilowatts per square meter. On optical flow methods, the optical flow method is based in this case on the optical flow equation developed by Liu and Chen, considering the optical flow for different flow visualizations, which is given by in terms of image coordinates, where in this case G represents the normalized image intensity, this proportional to the radiance received by the camera, and the U corresponds to the optical flow. In this case is the velocity, the vector of velocity that we have. In this case we have Ux and Uy, and V, F of X, Y, and G represents the boundary and diffusion term. Well, a variational formulation with the smoothness constraint is used to determine the optical flow according to this equation here, where lambda represents Lagrangian multiplier and omega is the image domain. The solution is found using the standard difference method with Neumann condition on the image domain. Well, images were collected with a high-speed camera were used to identify flow patterns during the tests. In this case here, in our experimental tests, we found 4 different flow patterns: bubbly, plug, slug, and churn flows. Here we have the example of bubbly flow in this figure here, the sequence of 2 different images. And here we have the result of the optical flow, considering in this case the global interface velocity field. The magnitude of the average velocity in the interface in this case is 1.1 centimeter per second, and it can be seen that the negative vectors are found in some points along the flow. Such behavior can be indication of a presence of vorticity in the liquid-vapor interface. Here we have the normalized velocity field along the flow. Due to the buoyancy effect, the bubbles are concentrated at the top of the channel, and the effect of viscosity causes variation on velocity profile. In this case, vortices mainly behind the bubble interfaces. Well, here we have an example of a plug flow pattern with a velocity field obtained from optical flow method. And in this case, the plug flow is identified with small dispersed bubbles along the flow. And here, in figure C, we can find the global intensity interface velocity field obtained from the analysis of both images. According to the results, the average velocity of the interface is roughly 1.5 centimeters per second. On the other hand, dispersed bubbles have an average velocity of 0.6 centimeters per second, indicating that the vapor phase does not present a constant velocity. The analysis of velocity field also indicate the presence of vorticity zones between plug and among dispersed bubbles. Such regions with vorticity can be caused cause fluctuations of pressure along the flow? Well, um, the slug pattern is characterized by as an oblong nose that protrudes into the core and dispersion of bubbles from the tail, as can be seen in this figure here. Fluctuations of a velocity field were also investigated along the x and y components in certain locations with fixed axial and radial directions. Here we can find, for example, the behavior observed in the x component of velocity at the axial position equal to 426 pixel, yeah, the red line. In this case, such a velocity profile is observed in the tail of the slug, where the bursting of bubbles creates regions with negative velocities. A churn flow regime was observed with a global interface in y component of velocity ranging from minus 1.8 centimeters per second to 1.8 centimeters at the radial position equal to 44 pixel along the flow in red line here. In fact, that's the center of the tube. The frequency of fluctuations in this component is caused by deformations of the interface, as can be seen here, and such deformations are result from Kelvin-Helmholtz instabilities. Well, the present investigation analyzed the liquid-vapor interface velocity with of flow patterns using image from a high-speed camera of full boiling of isobutane at saturation temperature of 70 Celsius degree, using a method based on the optical flow to determine the velocity fields and vorticity fields. And besides the components of velocity, vorticity was identified along the flows caused by different velocities on the interface, generating deformations of the patterns. Questions and suggestions, please email us, and thank you very much.